All right, so we're going to go ahead and draw a free body diagram of this box that is now being accelerated. I think the previous practice test I had it is moving at a constant velocity. So I'll actually do part A right here just to be careful. Now notice we have this force of 240 newtons pointing at 30 degrees. So I do want to make sure I include that in my, oh how cute, it never likes the arrowhead, in the free body diagram here. I'll have a normal force. I'll call it a tension this time. I called it an FA before. I just want to get used to seeing different names for these forces. I have the weight force, and I have a force of friction going like this. Now, the first thing I want to do is I want to split this into its respective components so that I can set up my force equation. So I have Tx, and here I have Ty. And just to be clear, this force is the vertical sine component, and this force is the horizontal cosine component. And we're actually going to use our vector algebra to help us figure that out. So a lot of people do this, and I really like it that people are doing this in their work. So right here, I'm going to write Ty is 240 times the sine of 30, and that'll give me 120 newtons. And we have Tx is 240 times the cosine of 30, which I believe is going to be about 208, but I just want to double check that math right now. So 208 times, 240 times the cosine of 30 indeed gives me 208 newtons of force. Excellent. So that is part A done. Now for part B, we're asked to calculate the size of the normal force on the box. And I'm seeing too many people simply say that the normal force is equal to the weight. And we need to be absolutely clear on how we calculate the normal force. The way we calculate the normal force is, once again, we're going to use these vertical components here. So that's going to be Fn plus Ty minus Fg, and all of those forces balance. Continuing, we're going to say that Fn plus 120 minus the gravity force, or the weight, which we can calculate as 60 times 10. So let's just be clear that Fg is in fact 600 newtons. And those forces balance. So finally, we're going to get a normal force value of 480 newtons. Excellent. Now, for part C, we want to go ahead and calculate the friction force opposing the motion of the box. To this end, we had to look at this system and realize we do have acceleration. So what this means is that we are unbalanced horizontally. So let's go ahead and set that up in part C. So we have Tx horizontally here, and force of friction going the opposite way. Remember, we always subtract the force of friction. That mnemonic, it's a terrible one, but it's just, friction's always trying to hold us back. It's always bringing negativity to the equation. Now, there are going to be some exceptions when you take advanced physics, but in this class, we're always going to subtract friction. So that's m times a, because we're unbalanced. So 208 minus the force of friction makes the 60 kilogram block accelerate at 2 meters per second squared. And so what that's going to do is it's going to get us a friction force equal to 88 newtons. Now for part D, we want the coefficient of kinetic friction. So we know that the kinetic friction here, it is kinetic because it's moving, is in fact equal to mu times the normal force, and that's mu kinetic. So we have 88 newtons equals mu kinetic times 480. So isolating mu kinetic, we're going to get a value of 88 divided by 480, which is 0.183. We'll worry about sig figs in subsequent units. All right, now for part E, suppose the string breaks. We want to calculate the time it takes to come to rest due to friction, assuming he was able to get the box up to the speed of 8 meters per second. So with that in mind, what we're going to say is, I'd love to use V equals AT plus U, okay? And we'll say 0 is A times T plus 8 here. Okay, so this is what we want to solve for. But the question is, what do we put in for acceleration? And to be clear, if I don't give you the acceleration, you have to solve using the free body diagram and forces. So in this case, we cut the string, and that means it no longer acts. So we have the normal force, we have the weight force, and we have the force of kinetic friction going this way. One small problem. You cannot use the result of part C because we no longer have a rope, and if we no longer have a rope, that is no longer affecting the normal force value. So let's first get the normal force by balancing forces vertically. So that's Fn minus 600 equals 0. So Fn is going to just end up being 600 newtons. Now let's get the force of kinetic friction. So the kinetic friction force, Ffk, is going to be mu k times Fn. My mu k is what I solved for in part D, so that's 0.183 times 600, which gives me about 110 newtons. Now, because friction opposes the motion, it's kind of like we have an applied force of 0 here. So I'll just say, always remember friction is negative in these force equations. So, and you know what? I'm going to actually write it like this. So we have negative force of friction equals m times a. That's negative 110 equals 60 times a. So a is going to end up being negative 1.83. Continuing. Now I can solve Suvat doing V. You know what? Let me just move this down here. Equals AT plus U. So that's 0 equals negative 1.83 times T plus 8. And T ends up being 4.4 seconds. All right, so that is problem number 11.